Hi everyone, in this video we're going to talk about dead people, which might sound a bit dodgy, but it's not really. Specifically, we're going to have a look at logarithmic functions. And where did dead people come in? Well, I'm glad you asked. Okay, so this is an actual formula that's actually really used. Let's go through it. So a coroner uses a formula derived from Newton's law of cooling. Okay, so Newton was a genius physics guy. He discovered gravity by an apple hitting him on the head, and the law of cooling is applied to lots of different kinds of contexts. But you can use it also to predict how long it has been since a person has died. Very CSI, I think. Here's the formula. T equals -10 ln. I'm going to come back to that in a second. That's a special log function. And inside the function we have t minus r base t over 37 minus r base t. And here's what they mean. T is equal to the body's measured temperature in degrees Celsius. R base T is the constant room temperature. So it assumes that that from time of death until when the body's discovered or whatever else, that the temperature hasn't changed. And T is the elapsed time in hours since death. Okay, so there's a little bit more information here. It says a more accurate estimate of the time of death is found by taking two readings and averaging the two calculated times of death. Okay, so let's have a look at the function. I'm just going to write it down on my screen and then I'll flick over to so you can see what I'm writing. So t equals -10 ln t minus r base t over 37 minus r base t. Okay, I shouldn't say base, I should just say subscript. Alright, so there it is there. Now, notice I use chord cursive for ln. That's just how I do it, because if I just go 1n, so if I just go ln like that, it kind of looks like a 1. Okay, so ln is one of those. It's a logarithmic function of a special base, and the base is e. It turns out that this special value e, which I can actually show you on the calculator, there you go, 2.7182. It turns out that that particular value is very common in population growths and decays in nature, and hence we call log base e the natural logarithm, and the shorthand for log base e, because it's so common, is ln. So when you see ln, it means log base e. But I'll call it ln. So -10 times ln, natural logarithm of t minus r base t, say that again, t minus r sub t over 37 minus r sub t. So that's the formula. And let's have a go at looking at some of these questions then. So the first question is, here we go. After a busy evening of Edpuzzle video creation, a maths teacher was found dead in his air-conditioned office. This isn't air-conditioned, so it can't be me, thank goodness. At 10 a.m., the coroner measured the body temperature to be 30 degrees Celsius. Okay. A second reading measured at noon found the body temperature to be 28 degrees Celsius. Assume that the room was a constant 21 degrees Celsius. Okay. So, what have we got there? Let's have a look at the first one. At 10 a.m., the coroner measured the body temperature to be 30 degrees Celsius. Okay, I'm writing it on my screen now and then I'll switch over. At 10 a.m., the body temperature was 30 degrees Celsius. Okay, let me flick over. There we go. So I've automatically just said capital T, because that was the body temperature, equals 30 degrees Celsius. Now the other fact we had was that the room was a constant 21 degrees Celsius. Okay, so R sub T is equal to 21 degrees Celsius. There we go. So that's our setup. So we should be able to work out what T is on that. So T is equal to -10 ln T is 30, so it's 30 minus 21 over 37 minus 21. That's okay, that's not too bad. Now, I should point out too that 37 degrees would be considered the average of what a regular human being body temperature would be when they're alive. That's where the 37 comes from. Let's calculate this then. Equals negative 10 ln. What's 30 minus 21? 9 over 37 minus 21, which is 16. So it's negative 10 ln 9 over 16. And we can get our calculator out and punch that in. So let's go 9 divided by 16 equals 0.5625. And then look on the calculator, and your scientific calculator will have one too. There's a natural logarithm button. There it is, ln. So when you do yours on your scientific calculator, you'd go log 9 divided by 16 close bracket. Give you the same thing. Sorry, not log, natural log. Okay, so click on that, and I get negative 5.75, and it goes on. So I'll say equals negative 10 times negative, sorry, you can't see that, negative 0.575, which equals, and then again, you can just do it in your head or multiply it by negative 10. 5.75, just to 2 decimal places. 5.75 hours. So at 10 a.m., we're saying the body looks to have been dead 5 3/4 hours. So what does that make it? So if 10 a.m. is when the body was discovered, then 5 hours earlier would be 5 a.m. and then 3/4 of an hour earlier would be, so the estimate, I suppose, is that the body is at the death occurred at 4:15 thereabouts. So 5 a.m. and then 45 minutes earlier, 4:15. But to confirm that, 2 hours later, so at 12 p.m, what did we have? T equals, so noon, 12 p.m. T equals 28 degrees Celsius. And room temperature hasn't changed, so R sub T is equal to 21 degrees Celsius. Okay, great. So let's work that out. T is equal to negative 10 ln of 28 minus 21 over 37 minus 21, which equals negative 10 ln of 7 over 16, which equals, let's have a look, use our calculator. So we have 7 over 16 equals, and then we'll take the natural logarithm of that. So it's negative 10 times negative 0.827. I'll flick that up here so we can see it a bit better. And we'll multiply that by negative 10. And again, you could just do this in your head, couldn't you? Just move that decimal point and make it positive, which equals 8.27 hours of death. Okay, so what have we got? So from 12 p.m. it was 8 hours earlier, and then another 0.27 of an hour. So 8 hours earlier from 12 p.m. would be 4, I think. Yep, 4 a.m. And then it's saying that it was another 0.27 hours. So if I just use 0.27 as a rough approximation and say 0.27 of 60 is equal to, let's say, 16 minutes then. So according to this, this would be time of death was, roughly 3:45 a.m.? Okay, roughly. So 8.25 hours. Okay, so what does that mean? Well, the first estimate was death at 4:15. The second estimate was death at 3:45. So the average between 3:45 and 4:15 is 4 o'clock in the morning. So the estimate would be death occurred at 4 a.m. I don't know why this maths teacher was making Edpuzzle videos at 4 o'clock in the morning, but it's clear that it's not good for your health if you do that. Okay, so there you go. So the estimated time of death to the nearest minute. Now, I was pretty rough there. It's really to the nearest quarter hour that I've done it, but that sort of, I hope, gives you an idea about how to do it. Okay. Now, for the next two problems, well, I'm not going to use averages again, even though that's what they actually do. I just want to really have a look at how the calculations pan out more than anything else. So let's have a look at number 2. It's a busy morning, and next door an English teacher was found dead in her air-conditioned office. If these are friends teachers, we clearly work too hard. Her room was a constant 18 degrees Celsius because she liked it quite cold. Maybe it made her think better, I don't know. She was found slumped over her keyboard, having just taken a screenshot. I mean, if I was dying, that's what I would do. The time on the screenshot was 3 a.m. So what would the temperature of her body be? Now, there may be some of you screaming out, well, how do you know she died just as she took the screenshot? You guys, shh, be quiet. Let's just pretend that that's actually what happened. So, screenshot was 3 a.m. What would the temperature of her body be? Okay, so let's assume that we're still talking about 10 a.m. That maybe it's a second coroner that's gone next door, because, you know, when you've got a double death in the in a school, you know, you usually have more than one coroner. That's the standard. Okay, so we'll assume it's 10 a.m. So number 2, let me flick over. Assume the body was discovered at 10 a.m. Then the time of the number of hours that have elapsed would be 7 hours, wouldn't it? So T equals 7 hours. 3 a.m. plus 7 equals 10 a.m. I think that's all right. It says that her room was a constant 18 degrees Celsius. So what would we expect the temperature of her body to be? All right. So R base T is 18 degrees Celsius, and T is the thing that we don't know. So let's set up the function. So T is 7 is equal to negative 10 times the natural logarithm of T minus 18 all over 37 minus 18. So let's simplify that right hand side a bit. Negative 10 natural logarithm of T minus 18 over 12 and 7 is 19. So over 19 degrees. Or over 19. Okay, so that's a little bit more simplified. Now, I'd like to use our understanding of logs in order to... I mean, we basically have to get at this T here. We can't get at it because it's inside, it's a parameter, it's a part of this function. So we have to unpick the function, and we can unpick that function by using our log rules, or the definition of a log, but we can't get at it because of this negative 10 here. So guess what we do? We get rid of the negative 10. We do that by dividing out because we know that there's a multiplication between negative 10 and the log. Okay, it's not written, but it's understood to be. So the opposite is to divide, and so I'm going to divide this side by negative 10 as well. So I've got negative 7/10. Now I know I'm going to be working with decimals here, so I think I might just cut my losses now and put the log over this side for a start. Ew, what was that? Oh my goodness me, let's try again. The log of t minus 18 over 19 is equal to negative 0.7. There we go, 7/10, negative 0.7. Alrighty, it is now time to work out what to do. We can use our definition of logs, right? So what we are going to do is simply express this logarithmic function as an exponential instead. So remember, natural log means log base e. So that means that e to the power of negative 0.7 is equal to t minus 18. So if you remember that log base a c equals b, then a to the b equals c. Okay, so in this case, a is e, b is negative 0.7, c is t minus 18 over 19. So I'll do that on the next page so we've got room, but I might need to flick a little bit to get it going. So what do we have? We have t minus 18 over 19 is equal to e to the power of negative 0.7. This is good news for us because we can calculate that. I might just keep it I won't evaluate e to the power of negative 0.7 because as soon as I do that, it's going to be a decimal approximation. So I might just keep everything nice and exact until the last minute. So first things first, I might do it in different colours so we can see what's going on. I'm going to times both sides by 19 because that will cancel out the 19s and leave me with t minus 18. And on the right hand side, I've got 19e to the power of negative 0.7. 19 times e to the power of negative 0.7. And then I'm going to add 18 to both sides because that will get rid of the 18 on the left hand side. So that will leave me with just t, the thing I'm looking for. And on the right hand side, I've got 19e to the power of negative 0.7 plus 18. Cool. What does that equal? You can see I've got a e to the power of x button. I've just got to be careful how I use it. So I go 19. So on your calculator, you would just do it in order. You go 19 times e, press the e to the power of button, and then press not. But I've got to do it in a slightly different order here. So 19 times, I've got to put the 0.7 in first, make it negative, and say use e to the power of x on it. There we go, nearly a half there, huh? Plus 18 equals 27.44. Okay, so I'll put that over there, just hide it out of the way a bit. So that equals 27.44 degrees Celsius. So that would be the temperature. So if they took the body temperature, that's what we would expect it to be, around 24-25 degrees Celsius after that many number of hours. Okay, that's that particular one done. Number 3. Let's say a corpse's body is 30 degrees Celsius cold in a room that's 10 degrees Celsius. How long would it take for the body temperature to halve? Now, why do we keep talking about it being a corpse? Well, because a live body has some ability to self-regulate, and you can run up and down, in the room to try and get a bit more energy and keep yourself a bit warm and all that kind of stuff. As soon as you've died, that self-regulation stops, and therefore the cooling, the body starts cooling, and hence the formula kicks in. So let's say it's 30 degrees Celsius in a room that's 10 degrees Celsius. How long would it take for the body temperature to halve? Okay, we can do that. So we have T equal to 30 degrees Celsius. Oops, daisy. 30 degrees Celsius, and we have R sub T is equal to 10 degrees Celsius. So let's work out what T. We don't actually really have to work out what T is exactly, because we're just after how long would it take for the body temperature to halve. So let's call T. Let's call the function T sub 1. And T sub 1 is whatever the number of hours is after death, such that the temperature of the body is 30 degrees Celsius when the room temperature is 10 degrees Celsius. Okay, so that would look like negative 10 ln T, which is 30, minus the room temperature, which is 10, over 37 minus 10. Okay, we can simplify that a bit, which equals negative 10 ln 30 minus 10, which is equal to 20, over 37 minus 10, which is 27. Okay, we'll just leave it there for the time being. Now, what about at T sub 0? So T sub 0 is the second time we're looking for. I've gone backwards in numbers because we're sort of going, I don't know, further. The temperature's dropping. Probably doesn't make sense to use 1 and 0 like I've used it. But anyway, it doesn't matter. T sub 0. So we start with the same formula, negative 10 ln. But this time, well, we're told, let's call that T sub 0. Then T sub 1, oops, wrong way around, huh? Let's match them up. That's T sub 1. What's T sub 0 then? T sub 0 is when the temperature's halved. It was 30 degrees. So we're saying, well, what's the temperature at 15 degrees? Room temperature is the same. Okay, so half of 30 is 15. So what have we got? We've got 15 minus 10 over 37 minus 10, which is 27. Okay, that's okay. That gives us minus 10 times the natural logarithm of 5 over 27. Alrighty, so we were after how many hours would it take for it to drop. So what I'm suggesting is what we do is we say then T1 minus T0 is the number of hours taken for body temperature to drop. Okay, so let's just say, for example, T1 ends up being, say, 5 hours after death, and then T0 is then 7 hours after death. Then we would say the difference in the hours is 2 hours. It takes 2 hours for it to halve. In fact, thinking on that further, it's probably better if I just use the other way around, huh? So if I say T0 minus T1, like so, is probably better. Okay, so what does that look like? What's T0 minus T1? T0 minus T1 is going to be negative 10 ln. What's T0? 5/27. Minus negative 10 ln 20/27. Like so. Okay, now I reckon we can do some clever things here. That's negative 10 ln 5/27 plus 10 ln 20/27. Alrighty, so if I take out a common factor of negative 10. I'm going to have ln 5/27 minus ln 10/27. 20/27. Oops. Okay, now, the reason why I took out that common factor of negative 10 is because I've now got two logs with the same base, log base e, and I've got two numbers that have been, the logs have been subtracted, which means that we can use the rule that that's equal to negative 10 ln, big brackets, 5/27 over 20/27. Okay, using that rule that we've looked at in class. Okay, well that should do some interesting things to us. Let's have a look. Now, I might just do this over here in the corner so you can sort of see. I'll just zoom up here so you can sort of see it. 5/27 over 20/27 is equal to 5/27 divided by 20/27, which is equal to 5/27 times 27 over 20. 27s cancel out, and 5 over 20 is, oops, 5 goes into 24 times, so it's 1/4. So that's equal to minus 10 ln 1/4. Okay, that we can put into our calculator quite happily. So bring Mr. Calculator back, and we can go 10 times 0.25 ln equals 13.86. So it takes 13.86 hours for the temperature to halve. We can convert that into hours and minutes if we want to, but we don't really need to. So 13.86 hours for the temperature of the corpse to halve from 30 degrees to 15 degrees. Now you can see I've got a second half of the question here. What about if the corpse's body was 20 degrees Celsius? How long would it take to halve then? So get to 10 degrees Celsius. Now, I'm not going to do this in this video, but that question might sound straightforward, but there's a little bit of a twist to it, which you might be able to think about. I'm not too sure, but I'll leave it as a question for you to have a go at, and might leave it as an open-ended question in Edpuzzle so that you can sort of put an answer in there, but you won't get an answer straight back on Edpuzzle, but that's okay. It's just for your thoughts, and then I'll correct them and talk about it in class. Okay, so that's where we'll leave the video. I didn't do a sketch, by the way, but I probably should have, just because you need to know how to do the sketches, but I'll leave that as maybe as an exercise for you to do as well. Yeah, perhaps you can figure out from this where it would cut through the x-axis, or the t-axis, I suppose, and have an idea about what that looks like. But maybe we might have a look at that in class as well. But that's enough talking from me, I think. Yep, that's it. Thanks.